Okay, so should I start, Francesca?
Go ahead.
Okay. So today I would like to present you guys peridynamic modeling of stress corrosion cracking. And as you see, I'm from University of Strathclyde in UK. Before I start, let me just give you an outline of my presentation. I will just briefly describe what stress corrosion cracking is, and then just briefly mention about our motivation of this work. And maybe this is the first time that you are hearing this terminology, peridynamic, so I will actually introduce you what that actually peridynamics is all about. And specifically, I will show you how we can actually use this new methodology to analyze a cubic crystal or polycrystalline type of materials. And then finally, I will show you actually how we can use this methodology for stress corrosion cracking problems. So when we talk about stress corrosion cracking, actually there are many different types of corrosion mechanisms. But when we say stress corrosion cracking, we need three things to come together so that stress corrosion cracking can occur. First of all, our materials should be corroded. And then we should have a corrosive environment, plus we also need to have a tensile loading. So once three things come together, we can see or experience stress corrosion cracking. And this particular phenomenon can occur in both brittle and non-brittle materials, and it's pretty dangerous because it can happen when we even apply 5% of the yield stress to the structure, and it can happen instantly. And as you can see on the right hand side, actually things are mainly happening at the mesoscale or microscopic scale, whichever the term that you are comfortable. So mainly our goal for this particular study is to come up with a numerical model, and this numerical model is based on a new formulation called peridynamics. And to do this, as I said, when we talk about stress corrosion cracking, we need to look at the things at the microscopic level. So, and this particular methodology is kind of new, and unfortunately we don't have all material models. So the first thing that we had to do is to come up with a new material model which can represent a cubic polycrystalline material. So after coming up with that particular material model, basically we also develop a multi-physics framework to couple hydrogen diffusion field and mechanical field, because there are too many or multiple stress corrosion mechanisms, and the one that we are particularly interested in this study is the hydrogen embrittlement. So before I move on to some more complicated concepts, so let me just briefly introduce you what peridynamics is all about. So peridynamics is basically a new continuum mechanics formulation. So why do we say new? Maybe Francesco may not like this because he's claiming that actually peridynamics is kind of a formulation that Piola came up with a long time ago, but not the term. Let's say at least the term is new. Exactly. So when we talk about Cauchy's continuum formulation that we now call classical continuum mechanics, normally that particular formulation is using partial differential equations. But in this formulation, we are using integral equations, and our equations, they don't have any derivative. So it is that without using a derivative in the formulation brings us several advantages, especially if you want to model fracture. So our equations are always working. So even if there's a fracture or not, they're always valid. So we don't need to come up with some external or extra conditions, or we don't have to use some additional type of formulations. And also, another nice thing about our formulations, we don't need to use crack-Roth law, which is not that easy to come up with, especially there is no universal crack-Roth law for which can be applied to all materials. And also, we are not treating cracks as special objects. Basically, they are part of our formulation, so we really don't care about cracks. So that means that actually multiple cracks can occur, and they can easily interact with each other. And last 3 talks, they were mainly on interfaces and so on. Again, we can actually specify interface properties in this particular formulation. So if you want to see, let's say, crack propagation through the interfaces, this may be a kind of a good approach. And also, although we are talking about continuum mechanics, we cannot solve our equations most of the time by using analytical techniques, so we have to use a numerical approach. Once we do that, most of the time we use meshless approach to do this. Our equations become very similar to a molecular dynamics type of equation. Although, as I said, still this is a continuum formulation. So we are hoping that since by using this similarity, it may be advantageous to link molecular dynamics and continuum formulation, so that it can be used for multi-scale analysis. As I said, when we talk about peridynamics, it's a continuum mechanics formulation, and we are just using the same continuum concept that other continuum mechanics formulations are using. So everything is made of these small volumes that we call material point. And many people just came up with the different type of formulations, and actually the most famous one is the one that Cauchy tried long time ago. But as I said, the continuum concept is the same, but the way that they describe the physics, or the way that they describe the behavior of the material point is different when we change from one formulation to another one. So according to Cauchy, he said that a material point can only interact with the material points in its nearest neighborhood. So they need to be in contact with each other. And to define this contact, actually, he just introduced these traction forces, so that these traction forces can transfer information from one material point to the neighboring one. And once we impose some physical laws, for instance, the global balance of linear momentum, and then if we express these traction vectors to the well-known stress tensor, we can obtain the equation of motion of a material point. So if we can solve this particular equation, we will have all the information, because this will tell us how the material point can move as the time progresses. So this is a beautiful equation, and people are trying to solve this equation for 200 years or so. But it has a little problem. The problem is basically we have a derivative term for this stress tensor. So what happens is, since the stress is related to strain and strain is related to displacement, whenever we have discontinuities, as in kind of a cracking case, this term is not valid, so we cannot define the term anymore. So that means that we cannot use this equation along the crack surfaces. So what happens is they came up with some other approaches to get around this problem. And in 2000, Dr. Stiversling came up with this term peridynamics, and then he introduced this formulation. And he said that if the problem is coming from equation, then why don't we change the equation? So that was kind of his idea. And also, when he came up with his new formulation, he also described how the material points are interacting with each other. So in this new formation, a material point can interact with all material points inside the body. And also the way that they are interacting is different. For instance, here is a force that we call peridynamic force that this material point is exerting on this, and this is the force that this material point is exerting on this. And as you see, they don't need to be in contact with each other. So this is one of the differences between this formulation and the Cauchy's formulation. And also we call this interaction as the peridynamic bond. So as I said, according to Dr. Silling's logic, because there is a problem in this particular term, he just kept all others the same, but he replaced this problematic term with a new term, with an integration. So basically, this term is describing us integration, or in a crude sense, summation of all forces acting on a particular material point. So, and as I will show you, this forcing term, or something that we call response function, does not contain any derivative. So that means that this formulation or this equation is always valid regardless of discontinuities. Now I just want to introduce you some important parameters that we are using in this particular formulation. So although I mentioned that a material point can interact with all material points inside the body, since most of the time we are doing a numerical calculation, if we take into account all these interactions, that will be computationally very challenging. So what we do is, we can assume that, if two material points, if they are too far from each other, the strength of the interaction should be pretty small. So that means that we can disregard many of these interactions. So what we do is, we are just introducing this influence domain that we call horizon, so that outside of this influence domain, we are assuming that there is no interaction. How about this bond force between 2 points? Actually, for a linear elastic isotropic material, you can consider this bond force as a spring force. But we are just writing this in a little bit different form. So instead of using a spring constant, we are using something called a bond constant times stretch. But as I said, it is very similar to a spring force. So how about the stretch? Stretch is basically the change in distance between two material points after the deformation, divided by the original distance between these two. So it's like a very similar, it has a similar definition to a strain in a one-dimensional bar. And our material constant that we call bond constant, and this can be represented in terms of the material constants of the classical continuum mechanics. So we don't need to do additional measurements to find that particular constant. So far, I didn't talk about failure, but introducing failure to the formulation is not that difficult. But we just need to be careful about the fracture behavior of our material. For instance, if our material is brittle, what we can do is we can always monitor our stretch value. So whenever the stretch value exceeds some critical value, then we can just break interactions, so that our force function between two material points can reduce to zero. So after that particular moment, there is no interaction between those points. So how do we calculate this critical parameter that we call critical stretch? It can be obtained in terms of fracture toughness. So again, something that we can measure. So breaking one interaction doesn't mean that you can create a crack surface. To create a crack surface, you need to break many of those. And also that particular kind of breakage only belongs to one particular interaction, so it has nothing to do with a particular material point. So to define the damage state of a material point, we are just defining this damage parameter. This is basically the number of broken interactions associated with a particular point divided by the number of original interactions. For instance, in the original state, this point is interacting with all points inside this horizon. Let's say after some time, some damage occurs and then we have some cracks, so that half of the interactions are broken. That means that now our damage parameter for this point is 0.5. But this is just an example, so it can be a number between 0 and 1. So, as I said, this is a new type of formulation. And whenever you are dealing with a new type of material, you need to come up with your new peridynamic material model to represent that particular material behavior. In this particular case, we were trying to use peridynamics to analyze cubic polycrystal materials. So we need to, again, somehow come up with a new material model. And polycrystalline materials are very common. So rocks, metals, and many ceramics, they are made of polycrystals, so they are important to analyze. And when we talk about polycrystals or crystalline type of materials, there are many different crystalline systems. And as I said, we are mainly focusing on cubic crystalline systems in this particular case. And when we talk about cubic crystal, this is the material matrix. So if you look at here, you see that we have three independent material constants, C11, C12, and C44. So to reduce our computational time, instead of modeling something in 3D, we just reduced our formulation to 2D so that we can obtain our solution in a much faster fashion. And now this is what we have. So we have only 3 by 3 material matrix in a two-dimensional sense. So if you are dealing with an isotropic material, we don't have any directional dependency. So you can have the same material constant everywhere. But this time, instead of 2 independent material constants, we have 3. So what we did is basically we just introduced a different material constant to the formulation, so that now we have 2 different bond constants. And these bond constants can be obtained again from the material constants of the classical quantum mechanics. So we don't need to measure them again. So before looking at the fracture, we just want to see that actually our material model is working properly. So what we did is we just, by using Voronoi type of approach, we came up with this random polycrystal pattern. And in a rectangular domain, we just fixed the left-hand side. We applied a tension loading at the right-hand side. And we were trying to capture the displacement field. So if there is no crack or fracture, our results should be the same with the classical formulation. So that's what we did. So we just compared the displacement field against finite element method, because finite element method is mostly depending on this classical formulation. Maybe it may not be that much visible to you, but as you see, our peridynamic results and finite element results along these central lines, they are on top of each other, showing that actually our material model can capture correct displacement behavior, so that we can look at the damage analysis. And then the next thing that we did basically is we just wanted to see how the cracks propagate. They can also initiate as well. Peridynamics can do that job. So we just considered a square specimen, and then we applied tension loading from the left-hand side and right-hand side. And we had 2 initial cracks at the top and bottom. And for polycrystals, the grain boundary behavior is important. And to represent or to analyze the effect of the grain boundary behavior, we introduced this parameter, this GBC. This is the grain boundary coefficient, which is the strength of the grain boundary. So whenever you see a value less than 1, that means we have a weak grain boundary. Whenever we see 1, it is our bulk properties and grain boundary properties, they are the same. And whenever you see 2, our grain boundary is stronger than the bulk properties. So we just want to see how the strength of the grain boundary affects the fracture behavior. We also look at the effect of grain size. So we just change the grain size to see how it influences the results. And also, in many cases, since we are doing a numerical analysis, again, we are doing some type of discretization, and we just want to make sure that the size of our discretization actually can give us consistent results. So we are just trying to find an optimum discretization size. So here, when we look at here, this is the coarser discretization, and this part is the finest discretization. And here we have different grain sizes when you go from the top and bottom. And in this particular case, we are analyzing a weaker grain boundary strength. And as I said, we are just applying a loading from the left hand side, right hand side. So we are just pulling this, and what happens is for different grain sizes we obtained optimum discretization, because after some particular discretization size we were able to obtain consistent result. And then what we did is we just did the same type of study for when we have the same grain boundary strength of the grain boundary strength and the bulk material, and when we have a stronger grain boundary, so that we were able to obtain all these fracture patterns. And actually, if you compare these results, what you can see is when we have a weaker grain boundary, we have lots of branching happening inside the material. So this kind of gives us an indication that if our grain boundary is weak, then our microstructure is really important. But if you look at the other cases that we have stronger grain boundaries, now what we see is basically, although we use a microscopic type of material model, the fracture pattern is something that we expect from a macroscopic model. So they are not really that much. The microscopic scale is not that much effective on the fracture behavior. And then what we did is we just investigated the case where we see the effect of microstructure, and so that when we have the weaker grain boundaries. And what happens is, although we apply tension loading from the left hand side and right hand side, as I said, for stronger grain boundaries, what we see is both of these cracks actually just propagate at the same time, in a parallel fashion. But in this case, as you see, the top crack didn't propagate, but the bottom crack actually propagates. And we were wondering about the reason behind this. And then once we look at what's happening at the grain level, it turns out that in some cases, the initial crack actually just crosses or becomes very close to our grain boundary, but in some cases it's inside the bulk material. So if our initial crack is close to the grain, the boundary, that means that actually this crack can easily propagate. But if it is inside the bulk grain, unfortunately that doesn't propagate. And then what happens is later on is, once you apply your loading, crack can occur somewhere here, and it can actually stop your initial crack. That is something known as macro crack cloud shielding mechanism. And this is something that we were able to capture by using peridynamics. And these are some fracture patterns that we obtained. So whenever we have weaker grain boundary, we were able to obtain intergranular type of fracture pattern. When you have stronger grain boundaries, what you obtain is basically we can capture intergranular fracture pattern. So we apply peridynamics for, as I mentioned earlier, for stress corrosion cracking analysis. And for this particular case, we just considered a very simple problem. Why? Because there is an experimental study for this, so that we can compare our numerical results. And this is our test specimen. We made of a high strength steel, and we have an initial crack somewhere here. And we are applying a displacement load at the top and bottom, and this is under static condition. And again, we just take into account the polycrystalline structure. And here we have a corrosive fluid inside of this crack, but the good thing is almost all of the surface is painted, so there is no influence of the corrosive fluid to the structure itself, but this tip is free. So it's not painted, so that the corrosive fluid can interact with the material itself at this particular crack tip. So what happens is, because of that corrosive fluid, actually this particular environment, this hydrogen starts diffusing the material as the time progresses. So once the hydrogen diffuses, although initially our crack is stable, stationary, the hydrogen makes our material much more brittle as the hydrogen diffuses inside the material, and later on the crack starts to propagate. And this is what we were trying to capture. And to represent this particular situation, we had to solve a coupled field equation. And the first equation is this hydrogen diffusion. So that's something that we need to solve. And we need to find out where like the amount of hydrogen diffusion inside the structure. And as the hydrogen diffuses, it makes our grain boundaries more and more weaker. And to capture that effect, basically we found this particle relationship from an ab initio or atomistic type of simulation. And so this is, we have this critical stretch parameter which dictates the failure, and it depends on this phi parameter, which is the hydrogen concentration. So it just depends on the amount of hydrogen. And although peridynamics, it was originally introduced for structural analysis, now we have peridynamic formulation of other fields. For example, this is the peridynamic form of a diffusion equation, so that you can solve multi-physics analysis in a single peridynamic framework. And we just considered 5 different loading cases. So what we did basically is we just considered 5 different displacement loading conditions. And each of these loading conditions, they are corresponding to a particular stress intensity factor that we calculated by using a finite element kind of analysis approach. And so for each of them, we just wanted to see when this crack will start to propagate, and then how it is going to propagate. So here, whenever we have the stress intensity factor which has a larger value, that means we have a large displacement. Whenever we have a stress intensity factor kind of small, that means we have a less amount of loading. So if you look at these results, actually they are kind of telling us how the hydrogen diffuses inside the material. So whenever we have a small loading, that means that it will take longer time for hydrogen to diffuse inside the body before cracks to propagate. And when we have a large load, that means, as you see, we have a very small region that hydrogen affects inside the structure before the crack starts to propagate. So this is basically the fracture initiation time versus the stress intensity factor. As I said, whenever we have small loading, the fracture starts to initiate much later, but whenever we have a higher load, then it starts to propagate much earlier. These are some fracture propagation pattern for a particular loading condition. So what happens is basically the crack starts to propagate, and then it just propagates through the grain boundaries, because we only allow the intergranular type of fracture pattern for this case. Something that we need to pay attention is when you do this simulation, once the crack starts to propagate, you need to update your boundary condition of your corrosive domain. So that because now you have new crack surfaces, so corrosive fluid should be pumped inside of this crack. So you need to just keep updating your boundary conditions. These are some fracture patterns for different loading conditions. So what we observed is, in some cases, the crack just propagates just by following a single crack pattern, but in some other cases, we see this branching type of behavior, something that was observed in experiments. And then what we did is, we compared our numerical results against an experimental study from these guys in Japan. And we just compared our crack propagation speed against our amount of loading. And as you see, our numerical results and experimental results, they match pretty well with each other. So far I just briefly showed you how we can actually use peridynamics to model hydrogen embrittlement, but also, although I will not show you in detail because of the time limitation, actually we are now using this technique to analyze other type of corrosion mechanisms. One of them is this pitting corrosion. And as you see, by using again peridynamics, you can capture very sophisticated pitting corrosion damage outcomes. And by using these pitting morphologies, actually you can also model this pit to crack transition situation, because since pit makes the part of the structure weak so that cracks can actually initiate from there. And again, something that we did by using peridynamics, so we are trying to capture the crack initiation and propagation from these pitting damage parts of the structure. So as a final remark, so what we basically did is we just came up with a new material model suitable for cubic crystals, and we were able to actually simulate hydrogen embrittlement or stress corrosion cracking process, and also by showing you some examples, I'm hoping that I was able to show that actually peridynamics can be a suitable tool for corrosion damage simulations. And with that, I just want to stop. Thank you very much for your attention. Good, very good.
Question. Your solution depends on the initial state of your material. Yes?
No. What do you mean? Maybe you can, if you can clarify.
Does not depend on initial state of your material.
That's correct.
No.
Maybe if you can. I don't understand the question.
Structure of the patches you have shown. This is influencing the crack process.
You mean the polycrystalline pattern? Is this well? Of course, they are affecting.
What about the uniqueness of your solution?
As I was trying to show you, we did a convergence analysis. So basically, by changing for the same crystal distribution, once you change the discretization size, we were able to obtain consistent results.
Okay, I explain. If you have homogeneous material and homogeneous deformation,
sure,
you have nothing. Yeah?
Sure.
Okay. Then we perturb only one point randomly.
Sure.
And then we perturb another one point randomly.
Sure.
This solution should be unique or not.
So what you're saying is we kind of randomly pick 2 points inside the material and we start the damage. Is this what you're saying? Or maybe
the answer to what you are asking is yes. Even if there is no general theory, the frame where it is moving is a frame in which well-postedness result is conceivable. I don't want to say there is a theorem like Sobolev, but the process is producing a unique evolution when you discretize. Of course, you need to know where the boundary of the grains are.
Okay, but
in all details.
This is
sure.
Yeah, but maybe we can talk
sure.
deeper in this point. Other questions?
It's a quick question.
Sure.
So you mentioned that your crack pattern by reducing the horizon size
yes.
converges.
Yes.
How about the crack propagation speed? Does it have sensitivity with respect to the horizon, or the speed itself is just not so sensitive?
It should not. If there is no length scale effect for that particular problem, it should not. Okay, so we should, in that particular case, we should use a horizon size as small as possible. Again, we need to do some type of a convergence study to analyze that.
Let us consider that your stage, which we can consider these materials as reversible processes. Reversible. Then have you some connections of your your model with maybe this field of defects. Field of defects is famous. Models which can be written using construct deformations, free deformations. The free deformation could not consider, could not connect it with displacement. The same defects, the field of defects. But this model of the field zero defects agreement with variational approach. Other words, if you introduce precipitate equations and boundary conditions, we can receive balance equations. And thus, if you introduce balance equations and kinematic relations, we introduce in equal way constitutive equations without subjectivity, because we have agreement connections with variational approach. But in your model, so much subjectivity is my mind. And what about agreement with some variational approach for reversible processes?
So I don't know if I understood your question correctly, but you can obtain our equations of motion by using Lagrange equation. So basically, you can start by writing the total energy of the kinetic energy of the system and the potential energy of the system of entire all material points inside the domain. And once you apply this to your Lagrange equation, you can obtain the equation of motion. So it is something again related to variational formulation.
It's maybe similar to your medium with field of defects. Is the same? No.
Maybe you should average, I think. I want to be polemical a little bit with this, not useful. Both Piola and Sealing found the variational formulation of this. Of course, you can introduce a dissipation when if the pair force F is not the derivative of a function, then it is not variational, and then you need a Rayleigh-Hamilton dissipation on the other side. But this is framed in variational way, and it is objective if appropriately formulated.
Yes.
Okay. So next.